All right, here we go. If you hear a bunch of noise in the background, it's because I'm covering a class, so it's not going to be quiet. In a different galaxy than ours, a different solar system exists with a sun that has a mass of this and an Earth-like planet with a mass of this that's this far away. What is the force between the two? Force of gravity is equal to G m1 m2 over r squared. And I know you're probably thinking, well, the sun has a radius and the Earth-like planet has a radius. But in this problem, they're so far apart that the radius doesn't even matter. It's like way out here, all right? So the sun, its mass is 2.33 times 10 to the 31st, and the planet, its mass, 6.98 times 10 to the 24th. The distance between them is 2.16 times 10 to the 11th meters. That's going to be squared. So what is the force of gravity between them? And punch it in, 6.67 EE11 negative times 2.33 EE31 times 6.98 EE24 divided by 2.16 EE11 squared equals, I got 2.32 times 10 to the 23rd newtons. Okay. What velocity would be necessary to orbit that planet? All right. So this thing's got to orbit it, and the distance is 2.16 times 10 to the 11th meters. So that's the radius. If we're looking at the velocity needed for orbit, velocity is equal to square root of g times the mass of the planet over the radius of orbit. So velocity is equal to square root of gm over r. M is the mass of the planet, not the, mass of the sun, not the planet. The mass of this thing doesn't matter. So the mass of that star is 2.33 times 10 to the 31st kilograms. So we're going to say 6.667 EE11 negative times 2.33 EE31 divided by 2.16 EE11 equals square root 84,823 meters per second. So 84,823 meters per second. All right, let's keep rolling. An Earth-like planet has a small moon with a mass of 4.5 times 10 to the 9 kilograms. What is the gravitational force between the moon and the planet? The total distance of orbit is this. So the Earth-like planet is this guy, 6.98. 6.98 times 10 to the 24th. So what is the gravity? So the force of gravity is equal to G. The Earth-like planet is 6.98 times 10 to the 24th. And the other moon is 4.5 times 10 to the 9th. And the distance between them is 1 times 10 to the 9th. And that's going to need to be squared. All right. We'll do this up. 6.67 EE11 negative times 6.98 EE24 times 4.5 EE9 equals divided by 1 EE9 squared equals I'm going to change this to scientific notation. 2.1 times 10 to the 6th newtons. That's the force of gravity. All right? All right. We're heading on a long journey. The spaceship is moving forward at 20,000 kilometers per hour. Let's convert that to meters per second. You would say 20,000 times 1,000 divided by 3,600. This changes it to meters. This changes it to seconds. So 20,000 times 1,000 divided by 3,600 equals 5,555.5 meters per second. That's cool. 5,555.5 meters per second. All right, that's our velocity. Space. The planet is this big. It passes by at this far. Will it be able to go by? Well, let's see. The velocity needed to orbit this planet is equal to the square root of g times the mass of the planet, 7.88 times 10 to the 29th, divided by the radius of orbit. It passes by at this distance, 6.83 times 10 to the 7th. And I know that you would like to take the radius of the planet in, but we don't know it, so we're just going to use this as the radius of orbit. Let's see what we would need. 6.67 EE11 negative times 7.88 EE29 divided by 6.83 EE7 equals square root. You would need to be going that fast to orbit that planet. So we would get sucked in and crash. You would get caught. All right? Here's why you'd have to go so fast. If there's no radius for the planet given, this is a super small radius. So this planet would be like super, super heavy, like 10,000 times heavier than the Earth, and you would be just barely missing the planet. This problem I'm not going to solve. It's just this. That's it. All right? That's it. There's the radius. Not going to solve that one. Let's keep moving. How much would you weigh on Jupiter? Okay. This is another just force of gravity. Gravity, 80 kilograms is the person. So 80 kilograms is one of the masses. And the other one is the mass of Jupiter. And then there's your radius squared. So it's just, this is the same problem. How many times heavier is he on Earth? Work the same problem, right? With G and then 80, and then Earth we know is 5.98 times 10 to the 24th. And then just divide the two numbers. All right, a wave is moving through air. The wave has a wavelength of this, 2.22, and a velocity of 314 meters per second. What is the frequency? 314 divided by 2.22. 314 divided by 2.22. 141.4. All right, great. Hertz. Remember, hertz is waves per second. This is the exact same problem as that one. All right? A wave is moving through the air. The wave has a wavelength of, we don't know, a frequency of 212 hertz, and a wavelength of 343. A velocity of 343. We're solving for wavelength. 343 divided by 212. 343 divided by 212 hertz. 1.6 meters is the wavelength, all right? Describe how the speed of sound changes in different mediums. It goes faster through more dense and slower through less dense. And none of this doesn't seem to be the case with air, but it's the case with everything else. Why is sonar for submarines and whales better than echolocation in air? Because the velocity of sound is higher in water, right? Draw and label a compressional wave. That's in your notes, okay? Compression, compression, compression. This is the rarefaction. Rarefaction, this distance is the wavelength. We'll be moving that way. Transverse wave looks like this. Crest, crest, trough, trough. That could be the wavelength, and that is the amplitude. The amplitude of a compressional wave is just putting more lines in there. That's the amplitude. And that controls the volume of whatever you would hear if it was sound. This is the time period is equal to 2 pi square root L over G. What length would you need for a 3-second time period? 3 seconds equals 2 pi square root L over 9.8 because we're on Earth. We're going to say opposite of times 2 pi is divided by 2 pi. Opposite of square root is squared, right? And then times 9.8. So you would, so this is going to be, let's see, 3 divided by 3 divided by 6.28 equals squared times 9.8. 2.23 or 2.24 meters is how long that pendulum would need to be. What time period would that same pendulum be on the moon? So if you had, what would the time period be if it was on the moon? So the length is now 2.24, and gravity is you put 1.67 because you're on the moon. So you would be like, 2.24 divided by 1.67 equals square root times 2 times pi equals 7.28. 7.28 seconds. That's how slow that clock would run on the moon.